Okay, so this is the last session. And in this talk, I will be talking about MPI4Spark, which is basically a high performance communication framework, that uses MPI. And Kenan right here, please raise your hand, is the guy who has done all the work, and I'm taking all the credit. So this is the sequence of presentation. So I'll just, I have some slides on the background, like why is Spark important and what is this new software stack called Netty. And then I'll talk about some of the motivation and challenges. We'll present the design and implementation, performance evaluation, and towards the end, I'll conclude. I think I don't need to motivate this slide, but one of the important workloads that has emerged is this big data analytics. And so our focus essentially has been that is it possible to utilize same communication or computation infrastructure for big data and HPC workloads? So we have invested a lot of effort, time, money, resources on developing the MUG'22 software. But if we have to, let's say, develop a parallel stack to support, let's say, big data or deep learning, that perhaps is not, resource efficient. Maybe it's a better way that somehow we can utilize the existing MPS, implementation or the API and MUG'22 specifically to support these big data stacks. So in this context, one of the important big data frameworks out there is the Apache Spark software. Another one of the other very important workloads is Dask, which is a very popular Python-based big data framework. And we are already supporting that using MPI through our MPI4Dask stack. So this is basically a parallel effort, similar effort to support Spark on top of MPI. And Spark's claim to fame is basically this in-memory data processing. So the older version of Spark, the so-called Hadoop software, had this inherent issue that if you were running iterative machine learning jobs or any big data jobs, you would run the jobs, the data would be in memory, you would write that back into the disk and then read it again. So instead of doing that, is it possible to maintain that data in the memory? And Spark basically provides a scalable solution for that. Spark has support for Scala programming language, Java programming language. They now support Python as well. And it also integrates well with many resource managers like Yarn and Mesos. And it has support for running streaming jobs, SQL, Graph, and MLDL workloads. But I mean, just like other parallel and distributed infrastructures, it is scalable, but it's also communication intensive. But if you go download Spark today, the vanilla Spark, it works on top of sockets, and that's essentially an opportunity for us to go and optimize. So one of the fundamental abstractions in Spark is resilient distributed data sets. So these are basically, the idea is pretty simple that, you just read the data, and you never go and modify it. Okay, you read the data, bring it into the memory from the disk, and you basically produce this new data and write another version of that onto the disk. And that's basically what resilient distributed data sets basically support. And this is what this so-called immutable is, that if you have a data set on the disk, you cannot go and modify it. If you want to modify it, you have the flexibility to do it, but you will read it, bring it into the memory, and produce this updated version back to the disk. And these are the kind of things that you can typically perform with RDDs. So on the left-hand side, we have these transformations. And then this is the left hand. On the left-hand side, we have, transformations. And on the right-hand side, we have these actions. So these transformations can be things like, doing map, filter. So filter is a good example, right? So all of us go through a lot of log files. We do greps. Okay, so basically you can filter, you can just, let's say, maybe you're looking for a particular line where you're looking for error 1, for example. So you would filter that, right? But doing the transformation is not going to go and produce a new data set. It's not going to basically commit back to the disk. So it's not basically going to be very compute intensive until and unless you basically do some kind of action. So what's the difference between transformations and actions? So transformations are basically, you have a version of data in the memory, you're transforming it, but you're not returning any results back to the user. So Spark would actually delay the execution until you perform any actions on the data set which is residing in the memory. If you're performing, transformations, it will keep a log of it, right? Because it can keep a log. It doesn't have to just instantly go and execute that action. The reason is it doesn't have to give the results back to the user. It has to give the results back to the user when you are actually performing some kind of, for example, actions. So for example, so we have a huge log file. I'm looking for error 1. I can say filter error 1, right? So this is not going to produce any action, right? So it's just an operation defined. I'll just maintain a graph for it. But let's say when I say, rdd.count, now I have to tell the user that, here was the input log file, and there are, so many lines that contain this particular statement, error 1, for example. So this is the support provided by Apache Spark for parallel execution. If we just look at the right-hand side here, so we have this master node, and then we have the driver node, and then we have these workers that can execute in parallel. So this is a fault-tolerant programming model. I mean, compared to MPI, so the workers can come and go. It will not affect the overall execution of your program. So if a worker fails, if you have assigned work to a worker and let's say it goes and fails, or if it is slow, the driver would know about it and it will simply go and launch a new worker. And in this case, if you see, I want you to focus on the first column of data here. So this is red column, then the green column, blue column, and then the orange column. So, the workers are going to distribute data with one another, right? So at the end of this sort of shuffle phase, which is the communication intensive part of Spark, each worker has a chunk of data from the other workers. So in the MPI world, we basically call it all-to-all, right? So basically something similar is also going on here. All the workers are communicating with one another. But if we go into the details of this, if we go, how Spark today is implementing this kind of communication, it's using point-to-point communication. And when we have converted this to use MPI, we are also using, point-to-point communication. We do get asked that, is it possible to utilize MPI all-to-all, for example, here? I mean, it's possible, but it will be a significant restructure of the existing Spark framework. So Spark actually relies on this piece of software called Netty. And Netty is essentially an asynchronous event-driven networking application framework. That's a mouthful. So under the hood, it basically uses Java new IO socket. So essentially, this is the architecture diagram of Netty. And it's basically using plain and old sockets. But this is very event-driven, right? So in MPI, the communication framework or the semantics is basically application-driven. The application knows that, this is the point where I'm going to call MPI receive, and this is the point where I'm going to send the data. I mean, we can actually achieve the same behavior by, let's say, using something like MPI probes or MPI probes, right? So what do MPI probe let us do? That, we check for incoming message. If I get the same, source and tag, only then I go and receive the message. But in this particular case, if you're let's say doing event driven networking application, you basically have callback functions, right? So you initially, when you start the execution, you get registered. So if a message of interest comes, basically a callback function gets called automatically. The application code doesn't need to do anything. It's all event-driven based. And this is one of the challenges that we have to deal with when we have to convert this essentially to utilize MPI-based communication. So some more motivation, again, I think I've conveyed this, that, our main motivation is that, there is socket-based communication going on. We want to utilize MPI communication here, right? And what this would allow us to do is that we'll be able to utilize existing high performance and low latency interconnects provided by HPC systems. So if you go on a lot of HPC systems today, take any supercomputing center, try and use Spark, you will be able to definitely use Spark, but it will be communicating using sockets, right? So that's, these low latency and high performance networks are already deployed there. So, we should be able to somehow utilize them. And obviously our goal is that we want to utilize, MPI functionality. And this is not to say that we are the first ones to do it, right? So we have an effort called RDMA-Spark. This is basically from our own group. And this utilizes RDMA-based communication inside Spark. But then in order to do this, we have a separate communication library for doing that, right? So which people in the group know that we call it Unified Communication Runtime. It's the UCR. But from our group's perspective, we have to maintain MUG'22, and then we have to maintain UCR separately. So that's not very resource efficient. Another notable software existing effort is Spark UCX, which uses Shuffle Manager, which basically supports Spark on top of the UCX communication library. So, but now so there is another project which is not here, which is called Spark Rapids or Rapid Spark. So that comes out of NVIDIA's Rapids project, and that basically supports GPU-based computation using Spark, and that also has support for high performance networks. But in that Rapid Spark project, which comes out of NVIDIA, that's not based on UCX. That's basically based on, they have, actually, I'm sorry, that's also based on UCX, but there is a different new code base, essentially, a new shuffle manager that works on top of the UCX communication library. So Spark UCX and Rapid Spark, they both work on top of the UCX communication library. But the cool thing about Rapid Spark is that it's the first framework that supports, in the Spark ecosystem, it supports GPU-based big data applications, and obviously it also supports GPU-based communication. So this is some comparisons with existing work. What I just want to emphasize is that there are different ways that we can come up with our solution, right? So for example, if we look at RDMA-Spark, they basically have an RDMA-based block transfer service. So this will actually make more sense when I show you the block diagram again. But the approach taken by, let's say, Spark UCX is that they have developed a new shuffle manager, right? So there is this concept of shuffle manager. Each shuffle manager has multiple block transfer services. The approach that we have taken in MPI4Spark is that we have not modified the code for shuffle managers, but we have written a new block transfer service which is based on MPI. Right, so, and this is perhaps the most important slide here. So I just want to emphasize, what's the challenges that we have to deal, right? So I think the first challenge here is that we have to launch the Spark environment from within an MPI environment. So the first challenge is we have to somehow convert Spark execution, the launching of drivers, all the workers, to basically become an MPI application. If you're launching an MPI application, you don't go launch processes one by one. You have MPI run RSH or MPI run or MPI exec. That launcher is basically going to do the job for you. But in Spark world, people don't launch applications that way. They either do it manually, or they will work with some kind of resource manager to do that. And then another challenge that we have to deal with is the Spark is very dynamic, and it will just dynamically launch processes. So for example, this is a Spark master, and then let's say we have 2 workers, right? So this basically setup exists before you launch any execution. And let's say now a job comes and the Spark master would execute a job for the end user. So this is what's going to happen. So a Spark driver process would be initiated, and the Spark driver process would contact the workers to launch these executors, right? So, and this is basically just a simple fork. So this worker 1 is forking executor 1, and worker 2 is forking executor 2. So the challenge for us, or Kenan to be specific, was that, how do we do this in MPI? And then the second challenge here is that, again, I've alluded to this before, that Spark is very event-driven, whereas MPI is application-driven, right? And then we also had this issue of, process naming, because when processes are communicating to one another using sockets, they have endpoints, they have channels, they have sockets. But in the case of MPI, we have MPI ranks. So I'll just explain how we are, tackling these challenges. So obviously, our solution is based on the MUG'22 library, and for this particular project, we also had to first come up with our own Java bindings. So on day 1, when I was presenting Java bindings, I promised you that we have a use case, a reason that why we are producing, these Java bindings, and essentially, the Spark MPI is our reason that we were doing that work. So here is some of the architecture. This is very high-level architecture. So I just want to explain this, that, beginning from the top, we have the application which is executing, and then we have Spark core. And this Spark core has this notion of shuffle manager. So sort is basically the default shuffle manager. And then it's possible to add new shuffle managers here, right? So this is the approach taken by Rapid Spark. They have actually written a new shuffle manager. But inside each shuffle manager, we have these block transfer services, right? So basically, the default shuffle manager, which is sort, uses this netty transport, service. So if you look at these raw orange boxes here, this is the server, netty server, and this is basically the netty client. So these are the two default ones. And they then rely on Java sockets interface, go over TCP, and whatever network is available. So our approach here was that we went with netty plus MPI transport service. So basically, we wrote a new transport server and a new transport client, and they would use our own Java bindings that would work over on top of MUG'22 using the Java native interface. And this is how basically we are dealing with this first challenge of launching Spark using MPI. And in this particular case, we utilize a DPM, right? So for example, if we just focus on step A, then step B, and step C. So I'll start from step A first. So we launch 4 wrapper processes, right? So basically, all of these belong to this default communicator, which is started by MPI process 0, 1, 2, and 3. And then each wrapper process then Spark are basically going to fork Spark processes. So for example, in this case, process 0 becomes worker A, process 1 becomes worker B, and process 2 becomes master, and process 3 becomes the driver. And basically, this is a simple fork system call that we are using inside these newly launched MPI processes. But at this point, all of these processes, they belong to the MPI COM world. But we need to start these executor processes. And we utilize DPM for that. In particular, MPI COM spawn multiple. And what's going to happen now is that the worker A and worker B processes, these will launch 2 new processes. Okay, and basically that's exactly what has happened here. So the COM world is staying the same. 2 new processes are launched, okay, which are executor A and executor B. So basically, executor A is executing on the same node as worker A, and executor B is executing on the same node as worker B, right? So this is clear. This is shown here in the node view here. But if you go into the details of how DPM works, so if we have launched 2 new processes, these newly launched processes now, they communicate over a new communicator that we call essentially DPM COM. And if if the processes in this newly launched DPM and the existing MPI COM world need to talk, so they will utilize this intercommunicate, right? So this is pretty complicated because now this executor A, it needs to communicate with executor B, and it also needs to communicate with, let's say, drivers, master, and the worker processes. And these, the processes in existing, COM world, they are already communicating with one another, right? So not only that we are communicating, but, we are also adding state. Executor A, if it's receiving data, it needs to check DPM COM, it needs to check intercom. So these two communicators are relevant for it. And if, let's say, if a master is communicating, the two relevant communicators here are COM world and intercom. So the first approach that we took was, this figure is complicated. What this is basically showing is this, the select system call, right? So if you have programmed with non-blocking sockets in C, so this select or select now function would make sense. But what this system call does is, if let's say if I am a process, I can register with multiple sockets, right? And then I don't have to go and call receive function. I will just say, I will just simply call select function. If I've received a message from any of the other process, I will be, a key will be generated. So I will go process that key. That key will tell me who was the sender, and it will also contain the message. So basically, this select function is driving the communication here. So in our first design, what we did was we converted this whole thing, which is event-driven thing, into MPI-based code. And the MPI-based code, would simply use the probe function. It will basically, it had a loop essentially, a while true loop, and it would just say go, it will do a non-blocking probe, and it will check, is there a message here, okay? And it will just continuously do this inside a while true loop. And all of us know while true loops are bad. And so this design was working. However, this it did not give us good results. It was too CPU intensive and it performed badly. So then I gave Kenan a little hard time and I told him that, we need to do something about it. So then we went into more details, and then we saw that, Spark is communicating all these different types of messages, right? And some of these messages are simply, maintaining the states that, are you available? Is the worker alive? But really, the shuffle messages were communicated as part of this chunk fetch request and chunk fetch success messages. And another message type that was interest to us was the stream response. So then what we did was, as part of this our so-called optimized design, that we did not modify much of the code of Spark, but we could identify inside the select loop when these two types of messages are coming, right? So, and in non-blocking functions, typically in non-blocking networking IO, typically you always receive a header followed by the body of the message, right? And the header of the message would give you information like, what's the type of message, how much data should you expect. So we basically kept, processing of that initial header in, in the existing Spark mechanism, but we only utilized MPI for this body of the message. And it turned out to be, significant because a lot of the data essentially comes as the body, and that is basically significant. So these are again some details. I will just skip these and go into the details of performance evaluation. So we have basically done our evaluation on Frontera system and Stampede 2 system, and then one of our own internal cluster. So the networks on all of these are different, especially the Stampede 2. This is Intel Omnipath, but because now we were relying on the native MPI library, so as long as the MPI library works, so we should be able to utilize the underlying network out there. So the first analysis that we did is compare the performance of NETI with our NETI plus MPI. So obviously, if you're doing if you're communicating messages on sockets versus you're doing communication on MPI, so that's bound to be much faster, and you definitely see that. So latency is 25x lower, and for large messages, this is like 9x better. So this basically makes sense. But really, the benefits, I mean, what we would like to quantify, or the success criteria should be that, does this lead to any performance gains at the application layer? So for that, we actually utilized two benchmarks, so Intel High Bench and OSU High BD benchmarks. So Intel High Bench is a pretty popular benchmark, and it covers a variety of data science MLDL workloads. And these are the performance results that we sort of get. So this is basically weak scaling evaluation with OSU High BD benchmarks. So in this case, we are basically running two benchmarks. One is what we call group by, and the second one is sort by. So again, we are dealing with large amounts of input data. We need to sort the data, or we need to group the data. So this is big data applications. So if you focus on this, let's say the left one first, because this is weak scaling, the problem size is increasing as we are increasing the number of cores. So for example, this is 8 workers, 16 workers, and then we have 32 workers, right? And each worker is utilizing approximately 50 to 56 cores. So in total, we are actually utilizing almost 1,800 CPU cores. And we are plotting 3 graphs here. So one is vanilla Spark. The second one is from our own lab, RDMA Spark, and then we have this MPI4Spark. And as you can see, for different runs, obviously this is MPI is, for example, for this group by application, we are getting around 2.1x speed up compared to RDMA Spark, and around 4x speed up compared to the vanilla Spark. We see similar gains for, let's say, sort by. So here, it's 3.4x against vanilla Spark and 1.7x against RDMA Spark. For strong scaling results, we see similar trends. So 3.7x and 2.1x for, let's say, group by, and for sort by, we also see similar performance gains. If we see the performance numbers on, so these are now different benchmarks from Intel High Bench. The first 2 graphs are from TAC Frontera, and the third one is from the Stampede 2 system. So for the first 2 graphs, we are plotting all the 3, Spark frameworks like Vanilla Spark, RDMA Spark, and MPI4Spark. But for the third one, we cannot run RDMA Spark because this is, OmniPath, and RDMA Spark will not work over here. And we basically see on average, 1.4x better performance than RDMA Spark. And for this second case, it's 1.4x on average, better than Vanilla Spark, and 1.5x on average than Vanilla Spark. Right, so we have basically talked about MPI4Spark in this talk, which is our MPI communication framework that utilizes MPI, and we have tried to introduce MPI-based enhancements at the NETI level. So before we started this, we thought that this is going to be a very modular, clean way that because Spark lies on NETI, and we'll make modifications to NETI, and then we don't have to make any modifications to, let's say, Spark. As long as we are making changes to NETI, any newer versions of Spark, we should be able to, let's say, make our changes to newer versions. But it turns out that Spark, the glue between Spark and NETI, it's not just that it's using NETI through an API. It's basically it's much more sort of intermingled than that. So which means that as part of this work, we have made enhancement to NETI but we have also made enhancements to the Spark code base. And we see good performance against vanilla Spark and RDMA Spark. We have tested this on TAC Frontera and Stampede 2 system. So we plan to release MPI4Spark in the near future. And we would also like to have support for GPU communication in the future. So thank you. I'm happy to answer any questions if there are any. So we'll be presenting this work in Cluster 22 next month.
So one quick question. The Spark programming model and MPI have like some semantic differences. So do you have any plans on addressing them? Do you plan to propose any kind of standardizations or things like that?
That's right. So, we'll be working very closely with you and the MUG'22 communication library, right? So if MUG'22 can work on top of a unified API, let's say UCR or, something similar to, let's say, UCX. So in that case, we don't need to work maybe on top of MUG'22. We can just go directly work on top of that, point-to-point communication API. And then I feel, then we'll basically bridge that gap.
Thank you.
Arpan.
Adam, you're quickly losing your position to Arpan, okay?
Yes.
As the person who asked the most questions.
We should have a reward for it. So is it possible to run Spark on GPUs?
It is possible to run. So the Rapid Spark project, right? So NVIDIA has worked with, what's the company behind Spark? Databricks, right? Databricks, and then they have a version of Spark that basically uses GPUs for, big data computation. So that had been a big, issue with the Spark ecosystem, that it was only utilizing CPUs for doing the computation work. Right. So, but now I feel, that has been addressed, and Rapid Spark would basically let you run big data applications using GPUs, and then it uses UCX for GPU to GPU communication, and that's our next target with MUG'22 GDR.
So you are going to improve MPI4Spark to include GPU support.
It will be a separate code base. So we'll work. Our starting point would be Rapid Spark. And we'll start with that and then introduce our own MPI changes into Rapid Spark.
Okay, thank you.
Well, Arpan, yesterday you worked for pretzels. Today you can work for cookies.
Yes.
Or you have
Unfortunately, chips. I can't eat it.
There is chips.
Yeah. Yeah, that would work. Thank you.
Bharat?
So have you profiled the different stages, like the communication time and other times in all the benchmarks you tried? Do you have like a split up?
We have. So I actually showed you the profiling information. I went quickly through it. So basically, in this case, for this group by, we are splitting, each bar into 3 stages. The names are really strange, but that's how the Spark web UI, shows that it's saying job 0 result stage, job 1 shuffle, and job 1 result stage. So really, the communication impact is being seen in this red part, right? So this is, this is light orange, and this is, medium orange, let's say. So if you focus on this IB over IB versus RDMA versus MPI, so the MPI version, you would see this red thing is reduced, has been reduced. So, and this is basically the shuffle communication.
Okay.
That has been reduced.
Okay, cool.
Yeah. Thank you. We can talk offline about it. We have 6 talks coming and we have 1 hour, right? So thank you. Thank you.
Likewise.